like signo, chlorine derivatives, which are used in this medicinal chemistry. As we know, medicinal chemistry is very useful and we can use various technologies to enable these properties. Also, he had explained the solar cells. As a electronics person, I know silicon is very useful in solar cells. The efficiency may be 20 to 25%. Now we explained 0.12% and it is increased up to 4 times, that is 0.43. But it is in the initial stages, so that it can increase and we can get very high efficient solar cells in the near future. Also, he had explained these anti-counterfeiting properties, and also he had explained the nanoparticles very well. Thank you very much. Also, the persons who have asked the questions and this technical session has been fruitful. Thank you.
Thank you, sir. I request Mr. Sujit Kurade, sir, to please come on dais and express the vote of thanks for this technical session.
Good morning, all of you. First of all, I would like to thank all students, research scholar, faculty member, those who are coming from other institutes, other colleges, and other states. I would like to thank here all the dignitaries, those who are present here today here for this two-day national seminar. So thank you very much, sir. Your presence is here today, because without your presence, the event is not possible. I would like to thank today's chairperson of this session, Professor Dr. P.P. Shah, sir. Thank you very much, sir. You came here and gave a valuable time for us for this event. Finally, I would like to thank today's resource person, Dr. R.R. Kamble, sir. Sir gave a valuable information about the medicinal chemistry, what is the use of medicinal chemistry in a daily life, how to synthesize the drug, and what is the applicative use of it in daily life. Sir also gave a valuable information about the solar cell, how it works, and what is the applicative use of it. So thank you very much, sir, for giving a valuable information about all these things which I have explained here today. So thank you very much.
Thank you, sir. Those are participants for oral presentation. Please collect their PPTs to Kurade, sir. Mr. Prashant Ghorpade, sir. Mr. Prashant Kamble, sir. Mr. Prashant Sarwalkar, sir. Please collect their PPTs. Sir, Professor, Department of Zoology, Devchand College, Arjunnagar, and Dr. S.T. Patil Sir, Associate Professor, Department of Physics, Devchand College, Arjunnagar, to occupy their chairs as referees.
हाँ बोला क्या था? हाँ इस वाले बोला क्या? हेलो बोला क्या? हेलो बोला क्या?
am working as a research scholar in a Department of School of Nanoscience and Biotechnology, Shivaji University Kolhapur. Today we have a presentation on azo dye absorption on a newly synthesized titanium doped the silica erosion by coagulation method and their comparative investigation with silica erosion and activated charcoal. So, first of all, what is erosion? Erosion is made up by two words. First one is aero, second one is a gel. Aero means air and gel means some part of solid and some part of liquid. Erosion is simply created by removing moisture from the gel while maintaining their original gel structure. It's like a hard styrofoam and it's known the only mankind lightest solid ever known to man. It is a highly porous and also known as a frozen smoke. Why it's also known as a frozen smoke? Because this looks like the smoke trapped in a glass jar. That's why it's also known as a frozen smoke. In figure 1, you can see here is the aerogel, and on the downside of the aerogel it is a flame which is around 600 or more temperature, and above it is a flower which doesn't affect due to temperature. Why that doesn't affect it? Because of there are many air pockets and highly porous structure. That's why we also know about that the air is a very bad conductor to thermal. It is a very bad thermal conductor. So that's why the flower doesn't affect by the flame or the temperature. In this slide, we simply explain soldier method for the preparation of aerogel. Simply when any metal alkoxide or metal salt precursor get hydrolysis, then it's formed colloidal salt. That means colloidal salt means it's a colloidal solution which is particle size 1 to 1000 nanometer. And after colloidal salt formation, it gets polycondensation due to some chemical atmosphere or environment. They get polycondensed and form a jelly-like structure, which contains many pockets which present the liquid form in it, and it is a strong network like structure which is formed. Then we simply dry down or spread on a substrate, then it gets gel formation. If we ambient dry, that means simply oven dried or air dried, then this structure or this jelly will be collapsed and form a dense ceramic structure. When we critically dried this material, then it gets aerogel form. That means their structure remain as it is or maintain their structure at that temperature and pressure. So that's why they are lightest material to maintain. I prepared firstly silica aerogel. Silica is simply prepared by using the tetraethyl orthosilicate precursor. That tetraethyl orthosilicate precursor get hydrolyzed. All we know that the hydrolysis means splitting of water molecules H plus and OH minus ions. That OH group from water get replaced this ethoxide group and formation of silicon and OH. That is a tetrahydroxysilane or silanol structure. And the remaining ethoxide group and H plus ions get as a byproduct of ethanol. So after that hydrolysis stage, the tetrahydroxysilane get further polycondensation reaction and get formed SiO-Si bridge-like structure. That is a silaxane bond chain, and then multiple bonds. They are not limited that direction. So that the chain-like structure will get expanded and form a network-like 3D structure. And formation of SiO-Si bridge. That is a SiO2 when we directly get annealed structure, or if we as it is used as for the application we known as a silica aerogel. That is a SiO-Si bridge get further formed. Then We also introduced in that silica structure, that was our novelty in this paper. We introduced the titanium in this structure for getting their more strength and increasing their potential for adsorption. So we introduced titanium in this structure. Therefore, we get the titanium isoproportional structure for titanium isopropoxide chemicals as a precursor for this reaction. And they further get hydrolysis and then so on polycondensation reaction. And they also similar bond formation with titanium in it. So that titanium gives their strength, also the increase their adsorption property we see in further. After the synthesis, we found that here is a 10 image of the synthesized materials. A to C is a pure silica aerogel, and D to F is a titanium doped silica aerogel. We see that there are some cavity present in it. I also present or regarding data about that porous structure is ranging, or that pore diameter is ranging between 2 to 50 nanometer. So the 2 to 50 nanometer is a critical pore diameter for that, because that size will absorb your any polluter like a heavy metal or dyes. So we only study the dyes, but it materials also the further application for heavy metals in rural areas. There are FSM images. We see the polymeric network-like structure. They bond together, and there is many smaller particles are linked together and form their chain-like structure. This is the EDS image of this synthesized material. We clearly see the Si and here is the SiO and Ti are present in our material. For the that gives for the simply conformation of the synthesized material. So in a FTIR we see the SiO which is a high intense peak are present in it, and that means it shows clearly the SiO which are successfully prepared in this or successfully formed in this structure. Then we see the TGA. When we study aerogel, the thermal their stability and thermal application are so low, because as a history of aerogel, first time aerogel is used in a NASA for as a coating techniques for coating as a coating for spacecrafts. So when the spacecraft goes above the atmosphere, temperature is more than 200, almost reaches 200 degrees Celsius. At that temperature, only aerogel materials are stable nowadays, and that's also lightweight and transparent are also the important properties in aerogel. So also we see that aerogel or our synthesized material are up to 1000 degrees Celsius are stable. There's a minimum 22% of weight loss are obtained up to 1000 degrees Celsius. So that means the material are stable up to 1000. That weight loss are due to the SiCH3 bond on the present on the surface of our structure, and that they goes on oxidation of this structure functional groups and form further the SiO bridge. But that loss due to only the SiCH3 bond, not our structure will be degraded. So as we see, the almost 78% weight are stable up to 1000 degrees Celsius. Then we also see the BET images or BET analysis of this material. We see that the pore diameter is ranging or lies between 2 to 50 nanometer. That means material over our mesoporous structure, and that was the ideal condition or ideal material for the adsorbent to interact these pollutant structures. So further we study XPS of this material, and we see and confirm the structure of SiO and titanium are present in our synthesized material. So after that we study that structure for methylene gluing crystal violet dyes. Why we choose these both chemicals? Because methylene blue are not easily degraded as well as a CVN. Both are azodized and highly toxic. So that's why we studied that both materials for the adsorption. And here we also comparative study with the activated charcoal. So first two graphs shows this is for activated charcoal on MBON activated charcoal. This is for CVN activated charcoal. And this is a pure silica aerogeneous graphs. And these are the our synthesized material, that is titanium doped silica aerogeneous. Further on, we also see this data in a tabular form. These are the isotherms, Langmuir, Friedrich and Temkin, who also we studied that we found that data or we observed that data. We are also included in this isotherms, and that are simply mathematical models which we proven or fitting our data with that their formulas like that. So as our result calculated found that around 131 mg per gram, that means 131 milligram of methylene blue are adsorbed on 1 gram of our aerogel structures. That is the highest we get, and also for CV is 159 milligram per gram of our titanium doped silica. And also we see that the Langmuir fit is more accurate, or R square regression coefficient is higher than above the three models, and also the chi-square is less than 1, almost less than 1. That's why it's fitted well, we know that from this database. There are kinetics. We studied the kinetics and we found that the pseudo second order reaction are suitable for this synthesized and all three structures we get it. And there is a mechanism. There are three main reasons why they are getting adsorbed on this. First thing was the pore structure. The pore structure is a 2 to 50 nanometer. Second thing was that the more active sites are present. More active sites. And third thing is the presence of OH group on it. The OH group, that is a negative ions present on the surface, that they easily adsorb. They are positive, that is a cationic dyes as methylene blue and crystal violet are easily adsorbed on the surface of synthesized materials. Also we study their recyclability use, because this study is important, because when you put this material in any commercialization units, the water purification techniques, we need to study further and further uses. Then simply not one-time use of this material. We need to further and further study of this material. So up to 4 cycles we studied, and almost more than 80% this shows their recyclability, and more show their efficiency up to 80%. So there are some comparative data we have found and similar structures. There is silica aerogel, almost 65 mg per gram maximum shows for I think there is a methylene blue dye at a pH 7. And when we study this, with our study, our research, we see that we get it up to 8 pH are more natural found when you dye pollutant taken from any real world samples. And our maximum adsorption shows the 131 mg per gram and 159 mg per gram. Also we studied more carbon aerogel and activated carbons. Activated carbon are also shows highest, but they not get further use or recyclability of their structure. So on all this database, I conclude that the TDS aerogel, that is a titanium doped silica aerogel, are mesoporous structure, and they shows almost 1.22 times higher than activated charcoal. Plus it is a recyclability up to 4 cycle and it more than 80%. Then it shows the pseudo second order kinetic reaction and is well fitted with the Langmuir isotherm. Langmuir isotherm also, there are significance of Langmuir isotherm. That means there are monolayer adsorption are occurred at that surface, dyes from aqueous solution with the potential wastewater treatment and further use for the commercialization purposes. Yes, sir. Aerosol, many papers are present online that they shows the air pollutant outside. So in China also the graphene aerosol are used for the air pollutant. Yes, sir. Possible it will be useful because they are porous structures, 2 to 50 nanometers that get easily incorporated or absorb the carbon and CO2 interaction. Titanium doses. Yes, sir. Yes, sir. Also, we study the biopolymers. Biopolymers shows the health strategy. I think some shows more. In PhD, we studied all the things. This is one of the chapters. I also studied the patches of cellulose and other aluminum.
Please keep silence.
For the adsorption. 19 minutes. Overall adsorption desorption equilibrium we get in 19 minutes. 19 minutes. Percentage. Almost 100% when we studied, almost, but not exactly 100 because some of the errors. We studied using UV visible spectroscopy. Some errors from the instrument also. I think it's 90.
First of all, you showed the PG characteristics.
Yes.
You have not mentioned the surface area of this.
Yes. I forgot to add that point. But I mentioned
So how much
that,
is the surface area?
for silica, it is a 450 meters square per gram, and for titanium dioxide, it gets 257 meters square per gram.
And in SEM you mentioned that there is some space which is responsible for adsorption.
Yes, sir. Here are some cavities.
I don't think so because the pores distribution and pore size is because of your grains. Yes, and not because of this. I think that gap is because of the just dispersion. Random distribution. Yeah, that is dispersion. Random distribution. You cannot claim it as a gap. Because your pore size is around
2 to 15.
what is that gap?
Around also, sir, 10 to 10.
No, it's very
I
high.
don't get
It's
it.
very high. Very high. And you claim that these dyes cannot be degraded. But there are a lot of literature
No,
available.
no, sir, I'm saying that they're degraded, but they are toxic. So if I mention that, I'm
yeah,
sorry,
they are
sir.
toxic, but most of literature is available on the degradation. Then what is the significance of your work about that photocatalysis?
So see, adsorption are very easy to operate technique than photocatalysis and other filtration, reverse osmosis and all other techniques. Because you get recyclability or reusability of the your filter or these things. And also, it is easy to use, that's why. And also many results, higher attention potential.
I would like to call upon the stage Preetam Borkar Madam for presentation.
Hello everyone, I am Dr. Preetam Borkar, Assistant Professor, Department of Chemistry in PS College of Arts and Science, Kolhapur, Goa. So today I am here to present my work on the topic Enhanced Photocatalytic Hydrogen Production under Visible Light. So here is the content: introduction, synthesis, characterization, photocatalytic study, analysis, determination of OH radical, antibacterial study, hydrogen production, use of hydrogen, and conclusion. Introduction to the topic. Now, day-to-day life, we see there are many types of pollution which goes on. So, wastewater treatment and energy crisis, these are the two main problems or alarming issues in the environment. And we have ample amount of sunlight which is available at least in India throughout the year. And there is a process called semiconductor photocatalysis, which is a promising method for using this sunlight and destruction of the pollutants which are present in the water. Okay. Also, it can be used for the production of hydrogen. Now, what is a photocatalyst? Photocatalyst is a substance which converts this sunlight into chemical light. Now, what is the difference between these photocatalysis and photosynthesis? You all know what is photosynthesis. We learn right from the school. Photosynthesis is a process by which plants prepare their food using carbon dioxide and water in presence of sunlight. And there is one important thing, that is a chlorophyll. And is just reverse of this process of photosynthesis. So in photocatalysis, what happens is a bigger molecule is broken down into smaller molecules with the use of sunlight and a substance called photocatalyst. So for this process, I have prepared a photocatalyst which is iron doped SnO2. For this, the synthesis was done by co-precipitation method, wherein the metal salts were dissolved and it was precipitated using sodium hydroxide. It was dried and decomposed at 400 degree for 2 hours. It was then characterized using various methods like XRD, IR, SEM, XPS, different types of techniques. So XRD result shows that SnO2 and the dope samples, iron dope samples, show same XRD pattern as the iron. It goes up to 0.3 or the 30% mole, it goes in the SnO2 crystal lattice and it gives a homogeneous solution, solid solution. Also, IR study shows that metal oxygen bonding is present between 1000 to 800 centimeter inverse. These are the same pictures and EDS pictures where it shows the presence of iron in the sample with the various morphology of the different composition. Also, the electrical resistivity was found to find out the semiconducting nature. Resistivity and the conductivity, they are inversely proportional. So as with increase in temperature, resistivity decreases, which means the conductivity increases. So these materials are semiconducting, they show semiconducting behavior. So this is one of the representative sample. One of the important thing in photocatalysis, that is to use the photo material as a photocatalyst, it has to have a band gap which can absorb the visible light, because as we use the sunlight, it contains major part of the visible light and only 5 to 8% of the UV light. So to use this visible light, the band gap has to be between 3 electron volt, and SnO2, it shows band gap of 3.57 and it is not able to absorb that much visible light. So the purpose was doping iron is to reduce the band gap which can use the visible light of the solar radiation. So with the iron doping, the band gap of the SnO2 gets reduced and it extends the absorption in the visible region. These are the XPS study results. XPS study result shows that iron is present in +3 state and Sn is present in +4 state. These are the photocatalytic study. One of the model dye, that is Congo red, was used. Absorption spectra was measured before the irradiation of light and with time, and then finally when the absorbance was reduced. So this absorption spectra shows with time how the dye gets degraded. And these are the graphs showing dye degradation at pH 7 and pH 10. So how we know the dye is degraded? There's a difference between just people say degradation and it is actually degraded. When the dye gets degraded with the sunlight and the semiconductor photocatalysis, dye gets degraded to carbon dioxide and water. So that is the main purpose of degradation. So the dye solution is a colored solution which is harmful. So it should be converted to harmless. So when it is degraded to carbon dioxide and water, it is harmless product. So that is how we get a harmless product after degradation. Also, the COD was measured before and after degradation. That is, COD is a chemical oxygen demand. Oxygen required for the oxidation of organic matter. So almost 90% decrease in COD value was observed, and also the carbon dioxide estimation was done. So which also shows increase in carbon dioxide value after degradation. Also, some of the qualitative analysis test shows that the dye is degraded and there are some ions which were present like NH4 plus, NO3 minus, SO4 minus 2. These ions were also detected. Stability of the photocatalyst was checked by recycling. That is, the reaction was carried out for almost 3 to 4 times using the same catalyst, and it was found that there is not much catalyst which is lost after the 4 cycle. Now the mechanism involves the presence of OH ions. As the semiconductor gets irradiated in the light, it gets excited and it gives electron hole pairs. These electrons remain in the conduction band and the holes remain in the valence band. And the holes, they convert this hydroxyl ion into hydroxyl radical, which is one of the important oxidizing agent. So this hydroxyl radical was estimated using terephthalic acid, and it combines with the OH ion and it shows the fluorescence, and with the time it shows the increase in intensity. So that is how mechanism was proved. Then also one more application was studied, that is the antibacterial study. Now as we know, the water also contains some microorganisms which cause waterborne disease. So along with the dye degradation, if there is a cure of these or removal of these bacteria, then it is well and good. So this material was checked for antibacterial activity, and it shows that this material, it shows the absence of this zone of growth of microorganisms. That means this material can be used as antibacterial agents. Then the next application was the hydrogen evolution, what we call as a green energy. So hydrogen, we have ample amount of water which needs to be populated. So there are various methods of water splitting, and one of these is photocatalytic water splitting using the sunlight. So experiments were carried out using water and the material which was prepared, and it was found that methanol can be used as a sacrificial agent, and also along with the methanol, if you use glucose solution in combination, then it gives faster results. So hydrogen which was evolved, now we cannot store that hydrogen as a fuel. It can be used as a fuel, but it was thought that just that thought came in mind that it can be used for the hydrogenation reaction. So this hydrogen which was evolved, it was used for the hydrogenation of curcumin, that is the ingredient which is present in the turmeric. So curcumin solution was prepared, and the generated hydrogen was passed over this curcumin solution along with the palladium carbon, and it was found that after 1 hour the curcumin solution was converted to tetrahydrocurcumin, and this was checked by absorption spectra or the absorption results. Tetrahydrocurcumin does not show absorption peak at 480, and curcumin shows at 480. Also it was done by TLC method, although I have not shown it here. So this hydrogen can be used for the hydrogenation of many reactions like curcumin, nitrobenzene can be converted to aniline. So like that we can do many reactions with these hydrogen. So summary of this, SnO2 can form solid solution with ion up to 0.3, and above 0.3 it shows both the phases. So only less amount, that is up to 0.3, can be added to the SnO2 crystal lattice. Particles can be found in nanometer range, and also these materials show semiconducting behavior. And semiconductor photocatalysis, it can be used as an efficient method for degradation of diaffluents, also for hydrogen generation. Ion doping improves the photocatalytic activity as the band gap is reduced and it extends the absorption to visible region. And the decrease in COD and increase in carbon dioxide shows that the dye is completely mineralized. Formation of hydroxyl radical outlines the photocatalytic mechanism. Antibacterial activity can be used to prevent the spread of waterborne diseases. And as this is a low cost technology which can be used for pollution control and reuse of water for different purposes like cleaning, cooling, irrigation, etc. And photocatalysis can be also used for generation of green energy. These are some of the references. Thank you.
These questions.
How do you recover the catalyst?
The solution was filtered. Solution was filtered.
It was soluble, no?
Catalyst is not soluble.
Okay.
Catalyst is not soluble. Catalyst is filtered off. It is again reactivated by keeping it oven for around 100 degree for half an hour to 1 hour, and it is reused. Or it can be also used by just pouring the solution and see other solution, similar solution can be added and used. So although there is a stability of these photocatalysts, but still we need some more methods like using the support material like glass material on which the photocatalyst can be coated and it can be reused. Thank you, sir. Yes, sir.
Continue with this question. How it is filtered as these are nanoparticles?
By using the Wattman filter papers.
So the pore size is very, they will pass as these are the nanoparticles.
Yes, but we get the amount is again calculated, means weighed. So there is not much loss in that. As I shown 100 to 80%, there is just decreasing 100 to 80 efficiency.
So I think it's better to use some membranes.
Yes, 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 sir, definitely.
Another question is that, see, in presentation it is a SN2 nanoparticle.
Yes, sir.
And every time you show SNFEO, it looks like it's a ferrite nanoparticle. So
SN, when we do Fe, 0.1 x, SN1 minus x, FeX. So x is that mole percentage. X is equal to 0.1 is 10 mole percent. So when we minus that 10 mole percent, here we minus it as SN 0.9. So it is Fe 0.1.
that is okay.
Yeah.
But the presentation, it looks like this is the ferrite nanoparticles. Because the Fe should be first and then SNO should be there.
So but usually this is written in this format only. Most of the papers it shows in this format. Hardly I have seen one or two where it is Fe was shown first. Means the dopant was shown first.
The dopant should be first.
Yeah, but usually in most of the papers they show as second, SN1 minus X.
Okay. And the last question is that the last slide you did hydrogen generation.
Yes.
So which procedure you did? Which electrode it is used?
No, it is photocatalytic. There is no electrode used. Electrode is for electrochemical.
So how do you determine the hydrogen?
Hydrogen is passed through GC. It is connected to GC, or it is collected and it is passed. It is given for GC estimation.
So how you collect the hydrogen? You don't have any assembly to collect the hydrogen to store.
Yeah, I have photochemical reactor.
No, to collection. How we can store the hydrogen?
The gas which comes out, it is collected in a gas-tight syringe.
Okay, syringe is there. So better if you have inline GC.
Yeah, I don't have inline GC. That's why this method was done, and that was given for estimation.
There will be loss when transport is to.
There may be slight loss, sir, because gas-tight syringe we use, immediately we take out. There may be, because we cannot say there is no loss. If it is connected directly, then it is well and good. But I did not get it. Although I had that funded projects, I did not get that much funds to get the GC. That was the thing. So that was given for estimation. Thank you, sir.
Madam, how it is enhanced? Enhanced.
Yeah.
How it is?
SNO2 shows if it is degradation, SNO2 takes more time for the degradation, around 4 hours. When Fe is used, time is reduced, and also the percentage is increased.
Therefore it is enhanced.
Yeah. because SnO2 takes less amount of visible light. When more amount of visible light is taken, absorbed, the process will be more faster. Band gap is reduced after adding iron.
It is the role of SN or AP.
Both, sir. SnO2 is a good photocatalyst.
You have written SN 0.9, then
Yes.
0.1,
Yes.
then SN 0.8.
Yes.
Then it is the role of SN or AP or both SN.
It is a role of SnO2, but when we add iron, it enhances the process. SnO2 is a good photocatalyst, but to enhance the process, we add Fe so that the process it gives faster results.
Both have roles, SN and AP.
Both will have roles. Because Fe reduces the band gap. That is how the process is enhanced. The purpose is to absorb the visible light. If we have to do it in UV light, we can just use plain SnO2. But since we are using it in sunlight contains major part of the visible light and UV part is just 5 to 8%. So that is how we are doping so that the major part of sunlight can be absorbed, visible light. Anything, sir? Thank you very much. I thank the organizing committee for giving me this chance to present my work. Thank you all.
Is anyone participant remaining for oral presentation? Please move forward. Please keep silence.
presence of imidazole nucleus, which is biologically accepted pharmacophore. Ammonium acetate, it is a catalyst which is non-toxic and stable, which is non-toxic and stable and widely used in the organic synthesis and easily catalyze multi-component condensation reactions. The compounds obtained from the pyrimidine exhibit a broad spectrum of pharmacological activity such as anti-inflammatory, antimicrobial, anti-HIV, anti-diabetic and anti-cancer activity. Now I would like to move towards my experimental work. Melting points are determined by using melting point apparatus in which we use open end capillary tubes. The IR spectra, the sample is now sent for the IR spectroscopy. The IR spectra will be recorded in the KBR palettes on a Nicolette 4D spectrometer, and Barnett NMR will be recorded in CDCl3 with a TMS as an internal standard. Purity of the, meanwhile, we go for the purity of the compound. Purity of the compound was checked by the TLC on pre-coated chromatoplate visualized in a UV cabinet. And the biological activities are predicted by using online and web-based computer program, that is PASS. In the present work, we have reported benzimidazole, 2-amino-benzimidazole, 4-ethoxybenzaldehyde and ethyl cyanoacetate with the catalytic amount of ammonium acetate in ethanol. The reaction is as shown in the screen, and we have equimolar quantities are used and irradiated in a scientific microwave oven for 3 minutes on a 20% power. The change in the color of the reaction mixture indicates the formation of product. While we pour this reaction mixture on ice, there is a formation of crystal and it indicates the compound is obtained. The compound obtained is as shown in this reaction mixture, and the product is confirmed again by the chromatoplates. This is the structure of the our desired product, that is 4-ethoxy 2,4-ethoxyphenyl dihydropyrimidone 1,2,8 benzimidazole 3-carbonitrile derivative. It is named as D1. Again, with the help of available aldehydes, and we have proceed for other products also. This is D1 structure, and by using PASS characteristic, we have designed drug designing approach we have discussed here. The structure of the compound is confirmed on the spectral data, and the confirmed structure when subjected to computer program PASS to predict biological activities. Synthesized the compound is found to be promising agent as a C/B2C12 substrate, and the similar protocols for available aldehydes is designed in the biological activities are predicted. Here P1, PA1, PA2, these are the biological activities predicted, and derivatives are D1, D2, D3, D4, etc. The first derivative is prominent towards PA2, that is anti-neoplastic. We have highlighted here, and for that we have given the graph structure. These are the different structures of the compound product D2, D3. Graphical presentation also given for the biological parameters. Lastly, I would gives some results. The use of ammonium acetate and ethanol is a convenient and cheap as it is non-toxic, and the synthesized derivative 2-amino-benzimidazole by using different aldehydes at para positions as are comparatively more reactive towards various diseases such as lung cancer, melanoma, viral and hypertension. And lastly, I would like to conclude, in the present work we have designed an efficient protocol for the synthesis of 5 derivatives of 2-amino-benzimidazole in the presence of cheap and easily available catalyst ammonium acetate. The reaction is carried out by using microwave, and it gets completed in a very short time period with the improved yield. By using conventional method, we are getting less amount of compound. The percentage of yield is near about 20 to 30%, but by the microwave assistance we get the improved yield that is near about 50%. So I would lastly I would thanks to DST for the grant section to our college to establish common instrumentation center. Thank you.
Is anyone question?
Microwave provides a constant or uniform heating due to dipolarization and ionic convection. Heating through the uniform heating process and time period condition. Immediately heating gets started.
What is the power you have mentioned watts?
20% power, sir. If there is a marking, we are just pressing the tabs. Marking is there, 20% power. But if required, we are converting into credits.
The heat is only due to the microwave.
No, sir, the reaction is carried.
Light contains compound. Only microwave.
Yes, in the present, in microwave we have carried out this reaction, sir. And conventional method, आपण काय करत होतो की just reaction reactant सोबत mix करत होतो आणि time period घालत होतो. In the presence of sunlight.
Microwave
मायक्रोवेव्हच का वापरला सर आपल्याला इझिली सध्या अवेलेबल होता आणि दुसरीकडं हे केलं कन्व्हेन्शनल मेथड कन्व्हेन्शनल मेथडने केलं तर 30% फक्त होतं सर आणि मायक्रोवेव्हला केल्यानंतर 50% आला. मी दुसऱ्या मेथड्स अजूनही फॉलो केलेल्या नाही आहेत म्हणजे कुठेही ट्रायल नाही केलेल्या. 3 minutes only, sir. Yes, sir. But sir is asking why the other methods are not employed. This is the significance which I had not referred. I want to tell you that I had not referred as the facilities. Sir, I have just mentioned here that conventional method is only 20%. Yes, sir. The next time I will take it.
Please keep silence.
You said ammonium acetate acts as a catalyst. How?
Ammonium.
Acetate is a catalyst.
Ammonium acetate in ethanol. In ethanol. Ammonium acetate in the ethanol.
We have added in the catalytic amount.
So how it acts as a catalyst? What is the catalytic mechanism?
Catalyst, it increases the rate.
That I know. Sometimes this also. But ammonium acetate, how it is acting here? This reacts as a catalyst. Is it interfering?
In the conventional method also we have used the ammonium acetate in ethanol as a catalyst, but the yield is only 20%. अँड म्हणजे इथं आपण अमोनियम एसिटेट इथेनॉल हे सगळं आहे, तसंच तीच रिएक्शन मी मायक्रोवेव्हला लावली. म्हणजे तिथं कॅटॅलिस्टमुळे रेट फक्त आपल्याला 20% मिळत होतं, पण टाइम पिरियड जास्त लागत होता. आपण आहे तेच पुन्हा ह्याच्यामध्ये वापरलं, मायक्रोवेव्हला वापरलं, ते टाइम पिरियड कमी झाला आणि यील्ड पण चांगला इम्प्रूव्ह मिळाला. म्हणजे तो कॅटॅलिटिकच काम केलं.
झाली असती, पण गिल्ड जर आपल्याला हे मिळालं असतं, कमी मिळालं असतं. गिल्ड झाली असते, सॉरी म्हणजे रिॲक्शन झाली असते, पण गिल्डचं पण कमी होतं. आणि कन्व्हेन्शनल मेथडला जेव्हा बघितलं त्याला 8 तास लागत होते. तर कॅटॅलिस्ट विदाउट कॅटॅलिस्ट मी जर वापरलं म्हणजे रिॲक्शन कॅरी केली 12 तास 14 तास, विच इज नॉट कन्व्हिनियंट. Pass program, we have not carried in the biological activities. We have just subjected the sample for computer-based programming. The work is in progress. We are sending.
Please keep silent.
The work is going on. We are sending the sample for biological activity, and then only we will predict. Within 3-4 days, I had find out this compound and just prepared for the presentation. So we are sending now in the next week for the biological activity.
Thank you, madam.
Thank you.
Now I would like to request Professor Dr. L.P. Lanka sir, please remark this oral presentation.
Well, good afternoon, one and all. Thanks to the organizing committee for giving me and my friend Dr. S.G. Patil sir to chair this session and to be the referee of this oral presentation session. And we were expecting more number of students to present their papers. Nevertheless, we had 3, but don't get disappointed because ranks are 1, 2 and 3. So those who have participated definitely will be getting either 1, 2 and 3, and we have assist, but later the results will be declared by the organizing committee, and it was good, and it was a good experience for the participants as well as the good experience to the students who are seated who are here, and definitely they are going to take something from today's conference, and you are going to implement in your day-to-day life. Thank you once and all, everyone, especially the organizing committee for giving this privilege. Thank you.
Now I would like to request Professor Dr. S.D. Patil sir, please remark this oral presentation.
Good afternoon all. I am not a core chemistry person, but organizers gave me an opportunity to assist the presentations. By giving assistance to Professor Lanka sir, we have assisted all 3 presentations based on effectiveness of PPTs, presentation style, content method, experimental work, characterization, results, responses to the questions. There are only 3 presentations, but overall response from all the presenters was very nice, and I am very much thankful to organizers for giving me an opportunity to assist this particular event. Thank you.
Thank you, sir. I request to Dr. A. Ramdege sir, please come on dais and express the vote of thanks for this session.
Thank you one and all. I am here to propose a vote of thanks to today's oral presentation referee Dr. L.P. Lanka sir and Dr. S.D. Patil sir. So on behalf of organizing committee and Department of Chemistry of Devchand College, Arjunnagar, thank you sir. And I would like to announce the next technical sessions continue Professor Dr. Lokesh Shastri sir. Over to
Thank you, sir. Dear delegates, we are commencing our fifth invited talk. I request to Dr. S.R. Sabre sir, Jaisingpur College, Jaisingpur, to chair the session. Thank you. This technical session is being graced by Speaker Dr. Lokesh Shastri sir. Now I request Dr. A. Ramteke sir to introduce the chairperson.
Okay. Now we are in technical session, last technical session of this today's national seminar. That is the invited talk fifth, Professor Lokesh Shastri sir. I am going to introduce the today's chairperson, Dr. Sandeep R. Sabre sir, who is a dynamic personality and is we are very much thankful and we feel a greatness because he is the alumni of this college. So I am just reading his biodata and you feel that greatness we have. Dr. S.R. Sabre has received his PhD in chemistry from Shivaji University Kolhapur, India during the period of 2006 and 2010. Postdoctorate study for School of Life Sciences, Shanghai University, Shanghai, China in 2014 and Pacific Northern National Laboratory, Richland, USA, America, 2017. Currently, he is working as Associate Professor in Analytical Chemistry at Jaisingpur College, Jaisingpur. He has successfully completed his administrative responsibility as the coordinator of DST field, coordinator of AQAC, coordinator of BOOK courses, which is the printing and publishing at Jaisingpur College. His research has included environmental science, photocatalyst, magnetic nanoparticles for hypothermia, biosensor and chromatography. Based on this research and fellowship training, he has received several awards and honors such as Departmental Research Fellowship from Shivaji University, Junior Research Fellowship from UGC, Research Associate Fellowship from BRNS and UGC Raman Fellowship, Postdoctoral Fellowship. He is serving as the editorial member of several reputed journals like Research Journals of Chemistry and Environment, Journals of Biodegradations and Bioremediations, World Research Journals of Physical Chemistry and Expert Reviewer for journals like Talenta, Hazardous Material, Electrochemical Communication, Indian Journals of Chemistry A, Chinese Journals of Chemistry, Journals of Environmental Chemistry and Ecotoxicology, Journals of Brazilian Chemistry Society, International Journal of Research in Chemistry and Environment. He has authored more than 75 research articles which have higher impact factor and high HIX. Also presented his work in international and national conferences in India and abroad also, like country USA, Tunisia, China, Sri Lanka, and many more. He is a member of Association of Separation Scientists and Technology, Indian Science Congress, Material Research Society of India. With this brief introductions, so number of academic and administrative responsibility on his shoulder, and he is successfully completed at Jaisingpur College, Jaisingpur. So we thanks to accepting our invitations for the chairpersons, and we feel great at this moment because the alumni we have for this chair the sessions of Professor Lokesh Shastri sir. Thank you, sir.
Thank you, sir. Now I would like to invite Dr. S.R. Sabre sir to introduce the honorable speaker of technical session.
Thank you, sir, for your introduction. First of all, I'm thankful to organizers for giving me this nice opportunity to chair this session. And this is my duty to introduce today's resource last session, Dr. Lokesh Shastri, who is working as an associate professor at Department of Chemistry, Karnataka University, Dharwad. Dr. Lokesh has completed his MSc as well as MPhil in organic chemistry from Karnataka University. Also, he has completed his PhD from Karnataka University, Dharwad, and the title was Synthetic Studies in Oxygen and Nitrogen Heterocycles. Before joining as an academician, he served in an industry which is a Syngene International, a biocon company located at Bangalore. And then since 2009, he joined Karnataka University, Dharwad as an assistant professor, and presently he is working as an associate professor. He has a good research experience. Around 7 students has completed a PhD under his able guidance, and 8 students are working for a PhD. He has awarded Best Research Paper Presentation, Outstanding Contribution in the Reviewing in the journal, European Journal of Medicinal Chemistry. He has completed 3 major projects from different funding agencies like UGC and DBT. 62 research publications are on his credit and 1 book chapter. Besides the research, he has different responsibilities as an academician, like coordinator of PG MSc in Analytical Chemistry, coordinator PG Science Evaluation, coordinator PGP MSc first and third semester, as well as coordinator PhD postdoc. With this brief introduction, I welcome you, sir, for this last session, and I request to present your work on synthesis drives for useful drug molecules through organocatalytic methods.
Now I would like to request Dr. Lokesh Shastri sir to give his invited talk on topic synthetic drives for useful drug molecules through organocatalytic methods.
Good afternoon to all. I thank Savya sir for his brief introductions, and I thank all the organizers giving me opportunity to present here. Now, something I prepared, but it is, I think, so looking into audience, I think it's somewhat like difficult. Okay, to justify this title, which is concerned synthetic drives for useful drug molecules through organic methods. The methods which you know, many synthetic methods which are presented, and literature that has been used and modified the useful drive for the easily to design such kind of molecules. Just catalyst, just I can brief informations I can share here. So what is the organic catalyst, which is there generally nowadays is using? It is a green source generally. You can use it as a green source, and you can recover such kind of catalyst, and you can recycle also, and less toxic. Among that which is there, devices is there, which you can call as a, what is that? Base is there, prostate acids, prostate bases. It is just categorized briefly. It is not an exact which is there, but somehow you can catalyze like that. And that's kind of this what you can call the catalyst. You can use some briefly I mentioned. It is not mandatory again, which I mentioned here. Which is mass is one. Mass is not.
cursor is not. Okay, no problem. Now this we can use organic catalyst methods. Briefly I mentioned here the reactions which you can use that organic catalyst. Earlier it was not like that because later on development when started the chemistry, specifically in organic chemistry, that organic catalyst has been developed. Organic catalyst has been developed and that has been utilized for many purposes. Many purposes. You can use it in psychological reactions, and earlier they used without organic catalyst. The product which is obtained all are non-stereoselective products which you observed it. That is, and halogenations, you can use it. Halogenations also, Michael reactions, Hack reactions, Navajan condensation reactions, aldol reactions, Diels-Alder reactions, many reactions, many more. You can use this methods to prepare required compounds. Now just one example, which you can see the examples, organic catalyst, Michael reactions. Earlier Michael reactions they done it, and which you obtain Michael reactions are non-stereoselective because Michael reactions, which you know, beta nucleophilic reactions end with the non-stereoselective product. Means both will get it either R and S component. Means racemic mixture, the various racemic mixture obtained. And this is one example how they modified later organic catalyst will get the more stereoselective, more than 95% enhanced selective products is obtaining if you use a organic catalyst. Organic catalyst, how that obtained later some experiments we done it. And now later one more is antimalarial agent, that's quinolines, which is more quinolines is used it here. And now if you use it without catalyst, you can use it some carbonate base also is there. Base also is there. If you use such kind of bases, which is generating chiral carbon, it's non-stereoactive chiral carbons we get. And if you use such kind of organic catalyst, which you can say the urea derivative of that and thiourea derivative, the product which is obtained is more than 97% enhanced selective product is obtained because of this selectivity of this catalyst that holds the stereochemistry properly. Now let's one more which is there. Now this is angstyrene which is there, that is used as a tonic and is treat elements like fevers, chloronic and diarrhea. And this dysentery also they use it. This kind of compounds which is there mainly, you know the chemistry because that stereoselectivity is how much important. If you have single isomers, that's better. And some compounds also have racemic mixture. Those kind of also molecules are better for the treatment. But some compounds we have specifically R molecule is required, means only R which is helpful. If it is there, that became poison. That will happen some changes in physiological systems. And such kind of molecules you can see here. That's quinolin angstyrene is prepared via using pyrrole which is there catalyst, and it is getting the more stereoselective the R product which is there. Now one more the organic catalyst method for the synthesis of amino isochromone systems. Those isochromone systems which is obtaining enantiomeric access is more than 95%. Yield is 92%. They use the catalyst like which you can proline with tetrazone systems. These are the organic catalyst structures which you can, and those products which is obtained, most of them are mycotoxics, which are the derivative of drug which is there in market, and which is there antibiotic, which is there called as a antidiabetic agent, which is also it is there, and insecticides and aldosterone synthesis inhibitors, which is responsible for most of the diabetes related drugs. Next, which you can see one more, that is benzoxazole derivative. Many are there in market, this kind of molecules which acts as a antiviral and antiparasitic activity. And that again now see looking into that it's this is chirality. You see the chirality, it's very important. And which is there the chiral systems, if it's coming below, that molecule is inactive, but the product obtained which is there above the plane of the systems, the product is active. But they use catalyst here, chloroquine catalyst is a chiral organic catalyst. And later many are synthesized from that, those are there in the market. And one more which is we can call as a proliferates, and with respect to drug which is there in the market, which is respective. And this is the responsible inhibitors of antidepressant the molecules. And the usually catalysts are there, organic catalysts for that. And they synthesize many steps. They use the many steps, 2 more steps, and they obtain such kind of And later one more synthesis of 3, which you can call as a spiro-indole derivatives, which are fused structures of tetrapyrans. And these kind of structures generally helpful. That's indole derivative, protein-protein interaction in habitus. Because overlapping of proteins makes much rigidity and it causes health disorders, and that's why you can avoid such kind of overlapping of proteins. Then you can use such kind of drugs, you can avoid inhibitions, such a overlapping of. And they use the proline derivative again modified as a catalyst, which is here it is there, this catalyst. Now, based on this which observations, many are the organic catalysts which are there. Chiral catalyst also is there, which is mentioned, and one more chiral catalyst also is there. In that main viewing in that observations, which you took the modifications of that proline derivatives of that one, we synthesize that chiral catalyst, and that is used for the later synthesis. And one of the drug which is there, these are again organocatalysts which you can use it. And now one which is there naturally occurring, the substance which is responsible for many things. And this is a warfarin, which you can see the warfarin structure and analogous of many warfarins. And this helps, it is a thinner, making the blood thinner. Generally you can call it as an anticoagulant. And this warfarin, which is their warfarin, this both R and S configuration having systems. R and S, and both are active equally. But when you compare among that, S is more active. But R and S there. But you can selectively do warfarin synthesis. The only approach which is earlier reported is a Michael reactions again, which is the below, which is their synthetic methods. And this is obtained is a recipe mixture. This compound which is obtained is a recipe mixture. And this compounds recipe mixture you can use it for the treatment of anticoagulants. And this has been discovered in 1932, and that is used for the what you can call as a thinning of the bloods, and that is nowadays still using as anticoagulant for the stroke which you are having. They use generally, this is the medicine which is there. And if you looking into that, we synthesize it using such kind of molecules, single molecules, such a warfarin analogous molecules have been synthesized. And this next, which is warfarin, how we use the synthesizing the catalyst single isomers, which you can see S-warfarin, which is more active S-warfarin, and they used, this is the imidazole, the tetrahydroimidazole carboxylic acid derivative has been used for the synthesis of such a warfarin. And that, looking into that, we synthesize, this is indirect methods because they use the direct methods via Michael reactions. Looking into this, the hydroxy group is there, and this carbonyl group it is there. All you are looking into that, the below which is presented, the indirect ring opening reactions we perform, and this is obtained is instead of just acetyl group, this is a carboxylic acid group is there here. There is no other name, but the beta positions, all aromatic system is there, and this side of coumarin is there. There is a mandatory for 4-hydroxycoumarin, that is one. And this is market, it is there in the market, the drug which is there, warfarin. And this is obtained, synthesized. We are using formic acid, but it is obtained is racemic mixture again, the compound which is there, racemic mixture. Later this we have modified. If you see the 3 component systems, the obtained product which is getting, that is pyran. The indirect method of warfarin synthesis, the obtained method is pyran, and that is racemic mixture again. It is racemic mixture, and that itself you opened and is getting the structure which is given 3. This is similar like warfarin. If you are looking to warfarin, and if you see this structure, we tried this synthesis using modified that instead of using straightforward Michael reactions or like 3 component systems, we made it here below. Just to condense that aldehyde groups, we made it dihydral systems, and which you can call as a 4-hydroxycoumarin, which you can see the 4-hydroxycoumarins, and it reacts with in presence of this catalyst which I showed in the red box, the red structure, and the obtained product which is there, pyrene, it is enantiomeric access is 93%. Enantiomeric access is 93%. And this 93% which is there, it is via, like it is not allowing to rotate carbon-carbon single bond, that catalyst holds it and leads the better structure which you have in single, and that is R structure which is there. And that has been opened and use the, which you can call as a warping-like structure, warping-like. And this is confirmed by its X-ray, and this is a chiral HPLC. Chiral HPLC which shows around 93% enantiomer access of this product which is obtained. Now this is pyrite. Now later similarly there is a dichromyl systems which is there, but you can modifications you started, that is thinking about that, and first we tested this compound whether it is shows similar property with comparison of that one. We studied many parameters, among that which use the ciprofloxacin as a standard because that is used as antibiotic also, and that ciprofloxacin shows around like 6.35 the micromole concentrations, which you can see the minimum inhibitor concentration of that one, and the synthesized compounds which are there here given, these are the better activity which is shown, and that they compared this one, the PDB which is there, PDB ID is used for that analysis, and the interactions which is there, similar interaction of this molecules with the ciprofloxacins which is showing the similar interactions, and that later these are the which you can until because that's showing anti-inflammatory activities, which you can call as a warfarin, and we studied the anti-inflammatory activities also that used in the standard is the acetylcholine, salicylic acid, that shows around 36.1 plus or minus, which is there deviations, and these molecules synthesized molecules shows almost double of that activity, and that which, and now it's not stopped because this is the dichromal systems which are there, all the structures which you can see the chromons. Instead of that chromium one which is there, you want to replace, you can replace the aroid systems which is requirement of that's warfarin, and that what you made here, instead of that coumarin one which is there red structure as showed, that is interacted with the what you can call the 4-hydroxycoumarin in presence of proline, which you can call L-proline, which is used as a catalyst, organic catalyst. But the end product is racemic mixture, means around 70% it is one is showing, one is less, which is now it is synthesized again. This is showing the mixture 49 and 50%. It is a chiral HPLC which shows that one. And what we made it, instead of that proline, we modified that structure. We made it corresponding. One more, the scaffold of that proline, that is sulfones which is there, PTS we taken and we made it modified that proline structure, and that proline structure has been used for the synthesis. And that time the product obtained is which is there, the chiral HPLC around 99%. The enantiomer access product which is obtained is 99% pure this compound. If you look into this structure, this one and this warfarin, it is almost similar, which you can see. Only the OH is which is the carboxylic acid, here acetyl group is there. Just modification, that is a single isomer which is obtained. And this single isomer has been confirmed by chiral HPLC is there, and later it confirmed because this is a methyl carbon, it is observed by DEPT, that you can see the methyl carbon and methylene carbon also, that is observed in one is negative mode and here is the positive mode of CH, which you can CH, methyl carbon. That confirms the structures which is there being opened warfarin-like analogous. And this which is later studied for this, and these are some compounds which shows better activity, and that we used the kit, that's COX-1 and COX-2, because which are to be responsible for the cleaning of the bloods also. That's why COX-1 and COX-2 utilize it to identify its property. And among all the compounds, these three compounds shows better. Now is the COX-1, it shows around 92, and COX-2 which is there, IC50 value, this all are representing in IC50 value, that shows at 21. And if you are looking into COX-1 and COX-2, here I given as per the standard, that shows around 500.3, 503, and one more is 121. It is almost around more than 20-fold, that's better than the what aspirin is showing. And it's showing many series of which is responsible for the anti-inflammatory properties. One is metalloproteins, which are there, MLP2 and MLP9. These are also responsible for, which you can call as a genothermic systems, that helps to how increase or decrease the property of that compounds. And later we studied the protein denature, because whenever antibiotic anti-inflammatory is happening, you have to see the protein denaturation also, and that is helps, and the IC50 value shows the better result for that. And these all are published, and we can see comparison with the docking studies of that molecules interactions, which use the standard aspirin sign, which you can say indomethacins, and comparison, it is binding very much similar like what the medicine market is there. That is bonding with which you can arginine 120, and similarly bonded with arginine 120 also. And it is again 120, again 120. The same amino acid sequence is binded with that molecules. And that shows that it is very similar, not identical, but very similar that what the standard molecule is showing. And that is, and then later this which is showing the aspirins. And now later on we modified the structures, which is there again antipyretic drug. This is linacozole. It is there in market in this name, linacozole structure. And if you looking into this our targets, it is required. Now carboxylic acid is there, pyrazole is there, carboxylic acid, pyrazole is there. Here is a chromol is there. Here arach system is there. And look into this linacozole. It also pyrazoles, carboxylic acid, and aromatic systems. And it's very similar like molecules. We plan to see this because we know how ring opening. Because there is no such molecules reported. You can indirectly, you can ring opening, you can do pyrans. Because most of the 1, 2 amino nitriles or amino ester systems, they constructed the ring-like pyrimidine structures. That are which are unique structures of DNA bases or RNA bases. Those are constructed. But in case when we heat with like acids, the ring opening is happening, and it is happening like the indirect beta arrivations, which you can see that beta arrivation structures means with respect to carboxylic acid, you can say there's beta arrivations of arach systems you are placing. It is not so easy to place on that because then later some molecules you made it, we will show it later. And these are marketed, which are there, all antipyretics and phenylbutazones and trimizones, all are there in market, and these are very similar molecules which you prepared and we studied the similar studies. And now similar now used such 3 compound structures and it's obtained the pyrazoles, pyranes, pyrazolopyranes, and this again if you see this structure, this is again recipic mixture. We studied this one, chiral HPLC, and again we showing the recipic mixture. And it is very difficult to separate. And then what we made it, instead of using such kind of DAMPO, this is non-chiral reagent, non-chiral organic reagent. Instead of that non-chiral reagent, you can use it chiral reagent like proline. That proline we used it, and the obtained again it is a recipic mixture, like we are getting around 40-60% the product which is there. Then what we thought it again we modify this one, the proline we converted this one diamine systems. We just used esters of proline and treated with hydrazine to end up with this green structure which is showing here, the catalyst, proline derivative of diaza systems is a catalyst. And that we run the reactions, these are 2 component reactions. I entered this which is there pyrazole. This is single which is there. This is a stereoselective product which is obtained, and the enantiomeric axis is around 99.36%. Enantiomeric axis is around 99.36%. That is single compound by chiral HPLC compound. And now we expected all the pyranopyranes. What I said is 1, 2 substitute amino and nitriles or amino esters on pyrazole here. Here, if it is such kind of compounds are there in literature, if you look at the literature, you treat such acids or any 1 carbon systems, either formaldehyde, either acyl amides or formic acids. If you use, all the time is end up with like such kind of structures. It is there in literature. But it is started thinking when you add acid, the compound is getting this one in this case. But they earlier they observed are not known, but this is where observed is a major compound in that, major compound. And that's why this chiral reagent used it and converted this is a single compound like linacozole like structure, and it's around same because there is no any change in this stereochemistry. As the pyra which we have pyrazole, there is ring opening, same stereochemical products will get it, stereoselective products, and that is what is obtained here. And this is confirmed by X-ray crystallography. And later this is studied its biological activity because we have compared that whatever the drug which is there, similarly the drug has been tested, used reciprocity standard which is there as an antibiotic, and it shows extremely good in both all which are positive and negative microbes used it, both in Saccharomyces and Bacillus, E. coli and Aeruginosa. This shows very good result when compared with the standard ciprofloxacins. And similar when it's showing antibiotic properties, and this also is performed because warfarin which is there is like antipyretic as well as anticoagulant and acts as a rapper. That's why we studied the anti-inflammatory studies also using acetyl salicylic acid, the inhibitions with erythrocytes, means red blood cells, which you can study that one, and that shows around 36.8, that is whatever the MIH value is there, that shows. And our compounds, most of our compounds shows it is around 55 to 50.26, means it is almost close to double of that activity shows. And this is which you can say bonding of that one, and it's a better PDB used, it's around which you can call as a 1A-D4. And similarly, this is the binding properties, which is what ciprofloxacin is binding very similarly, which you can origin 139 and ACL11, which you can call as cerium 50R. This is a very similar amino acids are binding with ciprofloxacin. And that says it's very close to which you can see used for the further developments. And these are similar binding systems. And how would we propose later? Again, one more structures. If you see Vanecazoles, we made the structures pyrazoles, which happens, and you perform these reactions, which is with proline, again receiving mixture of structures. Very similar, one more structure. And when you use structures, we propose the mechanism for that. We propose the mechanism for that, why it is happening, not in proline. Proline is not much interacted, but when you use such kind of one more modified organic catalyst, this is a which you can call PTH pyroline structures, and that leads to better enantiomeric access around 97%, which is proposed and now compared. And later this also is studied, the KIT study, which you can use the anti-inflammatory study that we can call as a COX-1 and COX-2, means that is cyclohexanase inhibitors 1 and 2, and that shows IC50 value. If you're looking into IC50 value, the aspirin, the green which I showed, and rest of the black I showed. If you compare that one, the synthesized compound is better than the aspirin what it is there. Now these are the molecules which are more active. Again, that inflammatory, which is similarly, it shows in the protein denature methods as well as inhibition of metalloproteins, which is 2 and 9. Okay. Now later on, this is there in hand the best protocol. We plan to make such a Reynolds derivative of that one, because that having two aryl systems, we want to place purely two aryl systems on pyrazoles, and that's why we made it like 1,3-diketones and transferred into that pyrazoles. Pyrazole is a target base molecule that we can utilize and we synthesize this one, and later we made Lanacolus analogs, and these we studied all structure activity relationship which are there related to anti-inflammatory, most of which are there responsible that anti-inflammatory will perform, and that which shows these are structure activity relationships. When you excellent potency, it shows R, which is deciding where it is the R is ester group, because the esters of aspirin it is there acetyl ester, that's why this we made ester here, the pink which I showed, and that shows the R is acid that exhibits better, means carboxylic acid. Similarly, aspirin also. Aspirin acetate which is there, that acetate is converted to corresponding carboxylic acid, that is the better inhibitors of COX-1 and COX always. But it is a acidic, definitely. And now later that is drawn with some docking studies, and very similar bonding, all the which are there amino acids are surround the molecules of standard aspirin. Similarly, these molecules also shows that. Okay. Now, which is there in literature, the synthesis of this which you can call as a baclofen. Baclofen generally they use it as muscle relief and injuries also, and some neurological problems which can treat this baclofen. It is there in market. If you go through this market, the synthesis of baclofen, it takes on more than 10 steps. Baclofen, if you synthesize this one, more than 10 steps it will take. First step which is there, Michael addition reactions, and the product which you obtain Michael addition product is non-stereoselective, and then you can separate. It is happening like that. You can separate. You want individual molecule, but baclofen is individual. Definitely, it is a single isomer, and that what they made it changes, and once they happening some kind of substitution changes all they made earlier, and that getting around like 70-30%, and 70 isomers they separating by prep HPLC, and that using corresponding salts, and they made it salts of baclofen and they are using. And now after development of organic catalyst, this which is called as diamino system organic catalyst, that has been used here, because this step is very important. Chirality, if you maintain, this step is very important, and that's why the chiral reagent is used here to add a Michael reactions, the stereoselectivity, and product which you obtain is purely stereoselective product, which is what you can call it, this esters. It is obtained in single isomer, and later on many molecules, because it is required amino acid NH2 carboxylic acid. These amino acids we can call as amino acid alpha, beta, gamma amino acid, aryl of alpha and gamma aryl acid, which is there is a becquerel salt that is. And now what we made it, because we have the idea the indirect method arylations or alkylations, because we require, now you see, from carboxylic acid or from nitro, there is a beta carbon. There is a beta carbon. If you count it from nitro group, there is a beta carbon, or if you count from the carboxylic acid, again it is a beta carbon. That is required for that becquerel, and that we have idea. We made it converted. This is indirect method of beta arrangement. This is the beta position with respect to both the carbonyl compounds. If you place in the beta here, it is not so easy on aliphatic system. Remember, sp3 carbon, it is very difficult to place alkylations or orylation on beta position. sp3 as such. Either you go like Michael reaction, product getting is non-stereoselective, you can use the organic catalyst. And that's why we made modifications, and this is beta arylation we done it, and now we prepared becquerel-like structure, very identical structure. If you place R is equal to Cl, it is a becquerel salt. Just prepare the salt. And here one which you can say indirect, because we prepared it is pyrene indirectly, the pyrene structure. If you want to prepare such kind of beta arylation products, the possible methods are there only. These are the reported methods which have taken place. Beta arylations, if you activate the beta carbons, use the petroleum catalyst, other many catalysts are there that you can use it. But the cost effective is more, and also the stereoselectivity is not worth. And now one more which is there reported in the literature. The second method which is there, beta arylation reported method is there, that takes around more than 8 steps to get this beta arylations, which is there the P which I mentioned below. In that pink reported methods which I said, that takes around 8 steps to prepare that. And it's so difficult because every step, loss of products, stereochemistry, everything involved in that, and it's not so easy to get that single compounds in after 8 steps. And that's what we made it here, this pathway, which is there, our reported methods, beta arylation, that was utilized, and that later, that's possible if you see the disconnection approach. If you see the disconnection approach to get the beta arylations, the possibility to do Michael reactions, pleasant condensation or pleasant reaction or aldol reactions. These are the two possibilities. You will end up with this product is non-stereoselective. And that's why what we made here, the structure we prepared again pyrene. We know ring opening is there, carboxylic acid is formed. That we prepared here, the pyrene, which is there, this structure, pyrene. And we just ring opening to made that, ring opening. And this ring opening, it happens to decarboxylation via and end up with such a beta arylated dicarbonyl compound. It is very pure compound. And but this is a racemic mixture because we are not, but use is a racemic mixture. And when you use the catalyst, which is there, pink structures are written here, pink structure, that is pure chiral compounds which you can use, and its obtained product is around 99.08%, 99.8% which is there. That is a pure single compound which is obtained, and that also it is R isomer. And that has been confirmed. It is not so easy. Again, it's confirmations we done it, and this shows called as a diselectivity, and it is DPT showing it is excellent for that comparison, and analysis has been performed. And this is next which is used in the market, that which is there earlier market, becquerel-like structure. If you look into becquerel-like structures, one more structure it is there in the market, that is fungicide. There is marketed based strawberry derivative, which is there in market. That is what you can call as isoxins methyl ester. This is one molecule. It is there. They are using as a fungicide. That is a fungicide structure. It is there in the market. And this is again isolation performing. It is difficult because handling of all those things. And later we thought if we can use them better instead of via that whatever the acid earlier reported which is there, this acid only, we can use and we can modify that. And what we done it here, that is whatever the ketones is formed, that ketone is condensed with oxygen, and this is exactly required ketoxins, its oxygen it is there, ester it is there. All skeletons which is there very identical, not much different, but it is close to that is a mimic structure like that. And that structure shows very better antifungal activity, which is there still, it is working on that. And the Agriculture University, Harvard. And now this, we drawn some conclusion for the fungal studies, and that fungal shows the better result for that. And now later, this asymmetric aldol reactions, and this is the reported, which you can see, reported methods. We required aldol reactions, later we used it for many purpose, the transformations, because it requires many oxygens, other things, anti-cancer drug, which is called as paclitaxel, it is there in market. Why are this method they proposed that one, and they ended with that. And one of that aldol reactions we perform. And this performed product which is obtained more than 95% enantiomer success. The use of proline is active. And these are the proposed mechanism for the transformations of the single compounds. Both here the catalyst here is used here, proline and derivative of what you can call as the phthalamide and proline derivative. They give same result. There is not much difference, which is proposed here transition state 1, transition 2, the product which is chiral products. And that has been confirmed using chiral HPLC. It shows around 97% enantiomeric access of that product. And this is confirmed also and by NMR, other instrumentation, spectral techniques, and even the single crystal X-ray also we propose this structure. And later some other structures which you use. Now why this I say, because warfarin we are concentrated here. We want to make it a group. That's why we went to aldol reaction, the pre-step which is there, aldol reactions, and after aldol reactions which is obtained, that OH is there, hydroxy group that converted to OH, means astair group, to make a living group and to get a single warfarin-like structures. And that's what we made here. Used the product aldol products and 4-hydroxycoumarins in presence of M morphine, and the obtained product, because the chirality is there, single molecule is there. If you do the SL2 reactions, the reverse of the product is formed, and that is what we expected definitely to obtain that product itself. That is here it is there. The structure which is a single compound which is obtained, and that has been again we analyzed the chiral HPLC. It shows around 96.2%. The enantiomeric access of that compound which is used, that is 96.2%, which is confirmed by that spectral analysis also. And this, if you know, that's chromone structures. Chromones which are always it's naturally occurring compounds, and this isochromones also is one of the major contributors for the antifungals and antibacterial antibiotics. And these are the structures which are now see mycotoxins and now aldosterone synthesis inhibitors. And this also prepared the product which is obtained in presence of carbonate, that is non-stereoselective. Non-stereoselective product is obtained. But when you perform these reactions using this chiral catalyst which are presented green, and the product which is obtained around 96% is enantiomeric access product, the single product, and that has been tested the fungal studies and microbial studies, which are bacterial studies, and which we also studied the anti-inflammatory activities also using a tetracycline as a standard. And when you compare the MM2 and MM9 with the tetracycline, the product which is isolated, it is somewhat very close to that tetracycline, and that we can use for further development. And later we made some changes, because most of these drugs which are there in market, that naturally occurring second generation, that is second line of anti-cancer molecules and antibiotic scaffolds. This is pyrophorins and nicostoropins and dihydrodaphthalin systems. These are all the second line anti-cancer drugs which are there, and now it is third phase clinical trial is going on. Now based on these structures, looking at the scaffolds, we plan to synthesis such kind of the furan with naphthalene structures, and which you completed and successfully synthesized also. But we have not studied the here what is called the selectivity. It forms dihydrosystems, no doubt, but we have not studied the use. But now it is going on the study on that chirality. But this mixture of compounds itself we tested, because this kind of compound shows better anti-cancer activity, and that's why we performed cytotoxicity, and the IC50 values it shows what used paclitaxel is 0.35 IC50 value, and some of our compounds which is there around 20 compounds we perform, and that shows around 3 or 4 compounds, it shows 0.28, and it is almost less than what ISBN value the standard is showing. Standard. And these are the which you can microbial studies structure active relationship drawn, and this structure active relation drawn is shown the groups variations. It shows excellent activity. And these are the interaction studies, and these are which we say biological studies which is shown as per that graphical presentation. The compound shows better than the standard which we used it here. And later one more structure which is there, anti-malarial drug agent, anti-malarial drug, which is most of the pyrimidine structures, and which is their corresponding names, which you can see that drugs which is designed. And similarly, we synthesize this structure, and this shows excellent activity comparatively the standard which is here. And which is more interesting organic chemistry because we tried this synthesis, because these are the antimalarial agent, the compound which is there, antimalarial agent, that is decovericins, which is there naturally occurring 8-membered ring or 9-membered rings are better always. And that's why we plan to synthesis which is there in nature, and we synthesize also. This synthesis decovericins is around 18 step synthesis is there. Later this has been modified, and the short route using devices is the organic catalyst, and they end up with this product which is there very similar like decovericins. But ring closures, the yield which is obtained in ring closure structures, decovericins, it is hard 10%. That's the one the drawback of this total synthesis, but short approach of synthesis we can do this synthesis of this one. And later one more, this is most of you know, it's what we tryptophan systems. Those are highly biologically active molecules, and it's anti-cancer, most of them, and that we prepared at 2 or 3 step synthesis, direct compositions, and we studied this one, and this study shows IC50 value, it is better. Now this kind of structures we showed, even if they permitted the biological innovation committee for the testing 2-3 times, but later at 3rd stage this has been rejected for the study. And later the interest of this print structure coumarins we propose, and this IC50 value shows around 1.1, which you get micromolar concentrations, which all activities performed in NSI USA. And later this is one more structure which is there because of this interest on Weil-Schillmann reactions which is there, because concentrated on asymmetric synthesis, which is the first step, it is Weil-Schillmann reactions. That have to be checked because these pyramidal structures are responsible for many activities. If it's a living structures like 1,3 nitrogens in most of the biological system, that is DNA and RNA, which is there. And this is the salt of this corresponding structures generally using as a eye drops, and many eye drops are related to this structures. It is there in market. And now this interested structures, but we lift it. Okay, I'm thinking this. Thank you.
Thank you, sir. Thank you very much, Dr. Lokesh Shastri, sir, for your valuable presentation. Now the session is open for discussion.
Yes, ma'am.
So nice, sir. Moving products. So what has been done for commercializing all?
No, it is not in our hand. If you want to commercialize, you have to take the patent. And if a patent is not marketed, then the money is, but nobody will pay that money, which is either university has to give, either we have to pay for maintaining that patent. But that has to take forward the institutes. Look into that, the institutes has to come forward and do such kind of patents, and every year you have to maintain that patent, and every year you have to pay for that money. And such an institute is not possible because the fees is so high every year around the patent, US patent, minimum I think it is 10 lakh rupees is there every year. Indian patent if you make it, and that is around 1 lakh rupees is there every year if you want to make maintenance of that. If marketed, fine. If it is not marketed, then you have to maintain that. That is how much. That's why people are not interested. Wherever come, they can give in the public domain. Somebody want, they can come and forward, and they can take and collaborate with the university, and they want to do, they can do it. It's not in our hand.
Any question? If there is no question, then I have one question, sir.
Please.
duration it will take to come that product in the market from synthesis to trials?
No, I cannot because compulsory said is over 8 years, but I worked in pharma company, it definitely is required. Because it's not so easy. Whenever you start the reactions, many problems will come. Many problems. R&D will do, that's fine. R&D if you perform up to that, preclinical trial, whatever you do now in vitro, that you can do it 1 year, 2 year, not a problem, you can come back. But when you register, if you take registrations, intellectual properties, then it starts thinking. And that what proposed method is there, it may not be work in bulk which you do in PRD. The method which you work in PRD, process development, you carry these reactions one after in vitro. Then you want to go in vivo. You want to go in vivo means the requirement of compound which is there synthesized, it is required high. Means it required 1 kg, 2 kg. And whatever we gram level we perform, that is obtaining 99%. If you perform in 100 gram or 50 gram, the nature of product obtaining is somewhat entirely different. The percentage impurity is coming in 1 gram, it is 5%, look in that, and 95% is compound is there. But when you go for the bulk production like 1 kg, 500 gram, you place it, the impurity and nature of reactions, everything, the parameters changes. That whatever the 5%, 0.5% impurity is there, that may increase, and that's why PRD takes much time. PRD, process development. Now we prepared it around more than 5 to 6 steps. Then PRD is required to minimize that steps to get back 2 or 3 steps. Because every step, if such a kind of chiral compounds are there, it is very difficult to manage. And that separations, purifications, everything will be difficult task. That's why they want to make it at 5 steps became 2 steps. And that 2 steps again they start R&D. Their own PRD people again they start R&D. And which is more convenient if it is not getting better. Because in PRD statement, when we give API molecules, that is one standard protocol is there. The impurity may not be less than 5. But got it? Means 99.5% compound has to be there, and whatever the 0.5% impurity is there, that may not be exceed less than, and single impurity may not be 0.5%. That is the API molecule standard protocol. And that if 0.5 which is there, it may be 0.2, 0.3 like it is there means no problem. If 0.5% itself impurity is there, that they want to start searching what it is there. That is a difficult task in PRD. Again they modify, again this will happen, so it starts and thinking. And once they started that one, if it's getting better, and then take carry forward for the in vivo test. In vivo test means that it requires hours in emissions, everything. For that time period testing, it requires around more than 3 to 4 years. 4 years to go preclinical trial. I am not saying final, preclinical trial.
So that is
this is many processes are there. It is not so easy.
So for pre-trials we need almost 3 to 4 years.
Definitely.
But we saw that the vaccine for corona. It will
that is the hybrid. That is hybrid. That is known compounds they mix with and that is
vaccine virus.
Vaccine is not a medicine. It is not a medicine. It is a vaccine. It is a mixed compounds.
But that also take more time to.
Of course. That's why taken around 9 months or 8 months. 8 months.
That is also more.
Just mixing, proportion of mixing the whole world is started with that, the mixing of compounds. There is no any single compound for the vaccine still today. That is there some compounds which are there since inception, whatever discovered, and there is some modification is done that. Other than nothing, there is no any scaffold which is there, basic skeleton remains as such it is there. There is no any means basic skeleton modifications. Just like ciprofloxacins, and if you see antibiotic of penicillin, all the modifications morphology made it, but not a basic skeleton.
No question. So I will conclude this session. So it was a systematic presentation by Dr. Lokesh, and he elaborated every aspect of chiral chemistry as well as organic catalysis, considering what is organic catalysis, the stereoselectivity, chiral drugs, and what is chiral and achiral catalyst. Even he elaborated warfarin as an anticoagulant as well as its other applications to it. So use of organic catalysis in synthetic single drug instead of racemic mixture. So sir, it's a really very informative lecture for our students. syllabus of organic chemistry. So I request my ma'am and sir to write a letter to the university for this good work. Thank you, sir, once again.
I request Ms. Reshma Dhuma Madam to please come on dais and express the vote of thanks for this technical session.
Good afternoon, all of you. I would like to thank today's chairperson, Dr. Sabde sir. Before behalf of Department of Chemistry, Devchand College, Arjunnagar, I would also like to thank Dr. Lokesh Shastri sir for sharing your valuable views on synthetic drives for useful drug molecule through organocatalytic methods. Your thoughts have enlightened our minds and have shown us a new path. Thank you very much, sir. Thank you, one and all.
Thank you, madam. Now it's time for signing the MOU of Department of Chemistry, Devchand College, Arjunnagar and KDCS Institute of Pharmacy, Uzraiwadi, Kolhapur. I request the principal, Dr. R.D. Hiremad, Mr. P.S. Salian, Mr. A.M. Berekar and Mr. P.D. Rajmane sir, please come on the stage. Now I request Professor Dr. S.S. Desai Madam to welcome the dignitaries. I request Professor Dr. S.S. Desai Madam to welcome Principal Dr. R.D. Hiremad, KDCS Institute of Pharmacy, Uzraiwadi, Kolhapur. I request Professor Dr. S.S. Desai Madam to welcome Mr. P.S. Salian sir, Lecturer, Selection Grade. I request Dr. Desai Madam to welcome Mr. A.M. Berekar sir as a Lecturer, Selection Grade. And now I request Professor Dr. Desai Madam to welcome Mr. P.D. Rajmane sir as a Lecturer, Senior Grade. Thank you, one and all.
Department of Chemistry, especially the Research Laboratory in Chemistry, is signing this memorandum between the two institutions, that is Kolhapur District Chemist Association's Institute of Pharmacy, Uzraiwadi, Kolhapur, and our department. The MOU is being signed at this particular moment. This is a brief introduction of this institution. Kolhapur District Chemist Association's Institute of Pharmacy, Uzraiwadi, was established in 1980 with the aim to create pharmacists well equipped with knowledge, skill, well trained and concerned about healthier society through their significant services. Institute believes that excellence and holistic development of pharmacists with continuous assessment of our students is of prime importance. Institute's main aim to assist the budding pharmacists in preparing for future challenges. For that, with existing state-of-art infrastructure, modern equipments and well-experienced dedicated faculty. So, I have also given the introduction of Devchand College in short regarding the research laboratory in chemistry, which is established in 2011. So far, 6 students have obtained their PhD from this particular research laboratory, of course under my guidance, and few more are working under the guidance of me and Professor Ramdeke sir. The thrust area of our research is heterocyclic chemistry, where we study the synthesis and biological significances of the various medicinally involved drug molecules. So purpose of this MOU, where both parties are agreeing to promote the following exchange activities like exchange of faculty and scholar, exchange of academic information and materials, collaboration with in periodical research publications, organization of joint research program, awareness program, training programs, as well as other academic exchanges agreed to by both colleges. There are also certain services to be exchanged like molecular docking and characterization of medicinal samples. थोडक्यामध्ये कॉलेज ऑफ फार्मसी जे कोल्हापूरमध्ये आहे उसळईवाडी येथे तिथे फार्मसीज चांगल्या क्वालिटीचे निर्माण करण्याचं काम होतं, जिथे अनेक प्रकारे आपल्या जे आम्ही सिंथेसाइज करतो रिसर्च लॅबोरेटरीमध्ये जे कंपाऊंड्स असतात त्याचा इम्पॉर्टन्स पाहण्यासाठी आम्हाला त्यांची मदत होईल. त्यांच्याकडे खूप एक्सपर्ट फॅकल्टी आहेत, त्यांच्याकडे वेगवेगळ्या पद्धतीचे एरियाज ऑफ एक्सपर्टाईज आहेत. त्याचा सगळ्याचा लाभ आपल्या स्टुडंट्सना व्हावा आणि आमच्याही रिसर्चमधलं थोडंसं कोलॅबरेशन आम्ही त्यांच्याबरोबर करू शकावं अशा उद्देशाने हा MOU केला आहे. मुद्दामून मराठीमध्ये आपल्या सर्व विद्यार्थ्यांना समजावं यासाठी असं MOU मेमोरँडम ऑफ अंडरस्टँडिंग हे दोन इन्स्टिट्यूट्समध्ये करावं असं चांगली गोष्ट असते, नॅकच्या दृष्टीने खूप महत्त्वाची असते. असं एक कोलॅबरेशन आपण करतोय. या कोलॅबरेशनची
थँक्स टू वन अँड ऑल.
त्यानंतर महत्त्वाचं म्हणजे लंच सेशन जाहीर होत आहे. तुम्ही सर्वांनी लंचला जायला हरकत नाही. त्यानंतर महत्त्वाचं सेशन म्हणजे व्हॅलिडिटी फंक्शन त्यानंतर लगेचच होईल. आता आपण 1:45ला लंचला जातोय.